Hello everyone, today I'm going to be showing you how I implemented Proximal Policy Optimization or PPO completely from scratch in Roblox. Roblox doesn't really have any built-in AI or reinforcement learning libraries, so everything you'll see here, the neural networks, the training loop, and the optimizer was written manually by me in Luau. This made the project a lot harder than using something like PyTorch, but it also forced me to really understand what PPO is doing under the hood instead of just calling library functions. And if you guys are wondering why I chose Roblox Studios, it's because I have some experience with it and I like the 3D environment so I can train agents easier even though it's much slower. Before getting into the code, I want to quickly explain how PPO works and why I keep using it in my projects. At a high level, PPO is a reinforcement learning algorithm that focuses a lot on stability. Instead of making big, risky updates whenever the agent gets a strong reward signal, PPO tries to make it smaller, more controlled changes to the policy over time. PPO is what's called an actor-critic method. The actor is the part of the network that decides what action to take, and the critic's job is to estimate how good the current situation is based on the actor's current behavior. The actor then learns from how much better or worse an action turned out compared to what the critic expected. One of the main reasons PPO works so well in practice is its clipped surrogate objective. Basically, it prevents the policy from changing too much in a single update, which helps avoid situations where learning completely breaks because of a few lucky or unlucky rewards. I chose PPO because this stability is especially important in environments like Roblox, where training is slow and rewards can be noisy. Even though PPO isn't always the fastest or most data efficient algorithm, it tends to keep improving over time without collapsing, which made it a really solid choice for my projects. With that idea in mind, I'll now walk through the main parts of my implementation and show how all of this is actually done in code. So this is the script. The variables you see on the left side are the hyperparameters or the parameters that describe the AI model. Here's the learning rate, which is how fast the AI learns. Here's the network structure. So currently the actor and the critic have the same neural network structure. And as you guys can see, you guys can add more layers to increase depth or increase the sizes to increase the width of the AI. And here are some batch sizes. So what this means is it describes how much data the AI collects before learning. And epochs is basically like how many times you reuse that data. You don't want it to be too high or else it overfits to that batch of data. Epsilon, gamma, and lambda are basically parameters for the general advantage estimate function and for the surrogate objective function. Gamma is basically how much to trust the future rewards, because normally you want to prioritize current rewards over future rewards. And lambda basically describes how trustworthy the critic's predictions are, because the critic isn't absolutely perfect in its predictions. So you gotta be like skeptical about that. So these are the parameters for the atom estimate function, which basically helps the AI learn more smoothly. And this is the entropy coefficient, which describes how much to reward the AI for being not too confident about something. So this is my get neural network function, which basically creates a neural network for us. So as you guys can see, we create each layer, and in each layer, we create the number of neurons for that layer. And then each neuron has a bias, which I set up between negative 0.1 and 0.1. And then the weights, I also initialized each of them the same. And then I stored it, and then I returned the whole neural network. So the activation functions I mainly use is ReLU, because ReLU is the most reliable and it's basically like the fastest and most efficient. It also doesn't have any vanishing gradients, meaning it doesn't like cap off at learning. So this is my forward pass function. So it basically takes in the neural network and inputs, and it stores the inputs in an activations. So basically it goes forwards in the neural network layer by layer and basically storing the activations. Each neuron will store its own activation, as you guys can see here, the first neuron. It's basically the bias plus all the weights that are multiplied by its corresponding input. So you got the bias here, and then you got the weights multiplied by the previous input going into that weight. And then we apply the ReLU activation, but we do not apply it to the final layer because we want the final output value to be whatever number we want, not capped. So ReLU would only make it positive numbers, but we don't want that cap. And then basically we just store it and return the activations. Okay, so this is my backpropagation function. It's a bit more complex, but what's basically happening here is this first loop is calculating the error for each of the neurons. And this loop over here calculates the derivatives for each weight. So basically how much to change each number to minimize the error. So this is my reward function, and it's pretty simple. It basically just rewards the tagger for getting closer to the runner. And I use an exponential function. That way the tagger's change in position matters more when it's closer to the runner. So make sure it wants to finish that task. Because normally it's easier to move when you're further away in the general direction, but when you're close, your movements have to be precise. And a big reward for when it actually tags the runner. Okay, so this is the main loop of my script. So basically it has a batch to store the data it collects. You first get inputs, and then you ask the actor, what should I choose? And the critic predicts how rewarding or what values it expects in the future. And then what we basically do is get the chances of the actor, because the actor outputs probabilities, and we want to turn that into chances which we can then use to select an action. So that's done here. And then the actor does the action and waits 1 second, or not 1 second, but 1 frame to let physics and everything render. And then you collect the reward. And then after that, you store it in the data, so the AI can use that later for training. And then that's basically it for the inference time. Then what we basically do is we calculate the TD errors, or basically how incorrect the critic was, or the surprise of the critic, in estimating the values that it believes the actor would receive. And then after that, we get the advantages, which is basically a more precise estimate which the actor will use for learning. Then we basically just normalize it, so it's easier for the actor to process, and it won't get surprised by any huge spikes or very low dips. Okay, this loop right here is basically the training loop. This is where the AI learns from the data. So for I equals 1 to epochs is basically how many times it reuses that data. Okay, so now the critic will forward pass to get the updated value. So then now the actor will output its what it thinks now it should do, And then this part gets the ratio, how much it has changed from its original policy. So because we're using PPO, we don't want that policy to change too much, which leads to unstable learning. So then that's where the PPO function comes in. And this basically tells us how much to change because we don't want it to change too much. And then we basically add the gradients into the full gradients for backprop. And then here we finally apply the gradients to the neural network. So there it has learned. Some functions that I don't fully understand yet, but I'm still learning about it, are like softmax, because I haven't really learned calculus yet, as I'm still in the 11th grade in high school. I'll be taking it next year in my senior year. Another more complex function that I don't fully understand yet is atom. What I do know about it is it basically estimates the momentum of the gradients, so that way it can skip those little bumps which are causing the AI to like slow down learning. So it basically speeds up and estimates the direction the AI should learn rather than having to follow each individual gradients, which can confuse the AI. And that's basically all. To wrap things up, I want to talk about some of the issues I ran into and what I like to improve going forwards. Earlier versions of my PPO implementations were a lot less stable, mainly because I didn't fully understand some of the key parts of PPO, especially the surrogate objective and how the gradients should be handled. Because of that, agents would often fail to converge or behave inconsistently even after long training runs. Over time, I fixed these mistakes through iteration and testing, and my current implementation now trains reliably and converges to a meaningful behavior. That process really showed me how important PPO stability mechanisms are in practice, not just on paper. There are still a few things I want to explore next. One is using a shared trunk with separate actor and critic heads, which would let both networks learn a common understanding of the environment and stay better aligned with each other. I'm also interested in experimenting with recurrent policies, such as LSTMs, to give the agent access to both short-term and long-term memory. The main challenge, though, would be implementing backpropagation through time efficiently. The reason for this is it requires much more memory and might be difficult within Roblox's constraints. Finally, I want to push self-play even further. For example, by training agents against past versions of themselves, which I did in previous videos, or using more structured tournament-style systems instead of using simple mirror matches. Overall, this project reflects what I currently understand about PPO. I hope you enjoyed it, and I'll see you next time.